Welcome to the DD1324 online lectures. In this lecture, we'll cover the topics of computer architecture, binary, and machine language. Let's begin with a look at how a modern computer system is organized. At the heart of the computer system is the processor. Connected to the processor through the motherboard are input devices like a keyboard or a mouse or the network, etc. Also connected to the processor through the motherboard are output devices like a computer monitor or a printer. You also have various forms of memory inside the computer, from very slow long-term storage like a hard drive, and as we move closer and closer to the processor, the memory becomes smaller and faster, going from the RAM to the L2 cache to the L1 cache. Of course, everybody knows that software is what runs on a computer, but there are different types of software. At the very high level, you have applications like your email client or a web browser, and lower level you have utilities like a printer driver. And below that you have the shell. A shell is a user interface for access to an operating system services. In general, the operating system shells use either command line interface or a graphical interface depending on the computer's role in the operation. And finally, at the lowest level, you have the operating system, such as Windows or Linux or OS X. Within the processor are several components as well. First, inside the processor, there are several high-speed storage locations called registers that temporarily hold data and instructions. Registers are part of a processor, not part of the memory or permanent storage. Processors have many different types of registers, each with a specific storage function. The register functions include storing the location where an instruction was fetched, storing an instruction while the control unit decodes it, and storing the data while the algorithmic logic unit computes it, and as well as storing the results of a calculation. You also have a control unit. The control unit is a component of the processor that directs and coordinates most of the processor and acts similar to a traffic light. It interprets each instruction issued by the program and initiates the appropriate action to carry out the instruction. Finally, you have the algorithmic logic unit. The algorithmic logic unit is a digital circuit that performs algorithmic and bitwise logic operations on integer binary numbers. A single CPU, FPU, or GPU may contain multiple algorithmic logic units. When talking about software, it's useful to clarify the difference between a program, an algorithm, software, and source code. A program is a set of instructions that performs a specific task when it's executed by a computer. Programs are written by a programmer in a programming language, and it's written in a human-readable source code form. From this, the computer generates machine code from a compiler or an interpreter, which it can execute directly on its hardware. An algorithm is a small part of a program that performs a well-defined task, and software is a collection of programs and their related data. It's common knowledge that computers operate on the binary or base 2 number system, but why is that? From a software perspective, there's no particular reason why binary should be used over the other base systems. Computers are built using the binary system for reasons that are tied to practical hardware issues. First, computers need to store and operate on data using physical devices, and electric circuits, specifically digital logic circuits, are an inexpensive and reliable way to do this. Using binary, it's easier to create control and logic circuits which are unambiguous. For example, using transistors, you can very easily determine whether or not the circuit is on or off, which can correspond to 1 or 0. They're simple to produce, they're cheap, and they can represent complex data with patterns of bits. In theory, it's possible for computers to have been built working in higher base systems such as decimal, but in practice, it's very difficult to build hardware that can distinguish between more than 2 states reliably. Therefore, from an engineering perspective, it makes the most sense to build computers to distinguish between on and off. In 1958, the Russians, however, developed a 3-valued system called ternary logic, which uses 3 states for calculations: +1, 0, and -1. It's useful to be able to understand the different ways that data are represented inside a binary computer. In a normal binary computer, the common ways are using the binary system, or base 2, which contains the digits 0 and 1, the decimal system or base 10, which contains the digits 0 through 9, and the hexadecimal system or base 16, which contains the digits 0 through 9, and then A through F, where A corresponds to 10, B to 11, and so on up until F is 15. It's possible to convert between any of these number systems using the following formulation. A number in base system B, written as an minus 1, ... all the way down to a0, has a value of an times b to the n plus an minus 1 times b to the n minus 1, all the way down to a0 times b to the 0. So if we want to convert 1001 in binary to decimal, which is 9, this is done by 1 times 2 to the 3, which is 8, plus 0 plus 0 plus 1 times 2 to the 0, which is 1. 8 plus 1 gives you 9. The number XABBA in hexadecimal, where X denotes that it's a hexadecimal number, and the number is actually ABBA, is equal to 43,962 in decimal. And we can convert this using the following formulation. So A is 10 times 16 to the 3, that gives us 40,960. B is 11 times 16 to the 2, that gives us 2,816, plus 11, or B is 11 times 16 to the 1, that gives you 176, and then plus A is 10 times 16 to the 0, and that's 10. So 10 plus 176 plus 2,816 plus 40,960 gives you 43,962. A bit, or a binary digit, is a fundamental unit of information storage. When we talk about the number of bits, what we're saying is the number of digits in a binary number. For example, if we say a number has 1 bit, that means it's the binary number 1 or 0, and it can be represented in decimal as 1 or 0 using the exponent polynomial expression 1 times 2 to the 0 or 0 times 2 to the 0. If we have an 8-bit number, that means we have a binary number with 8 places, and it can represent decimal numbers from 0 to 255 using the polynomials 2 to the 0 to 2 to the 7. Most modern computers are 64 bits, which means they're binary numbers with 64 places, and the decimal number that they can represent goes up to 9.22 times 10 to the 18 using the polynomial exponents 2 to the 0 to 2 to the 63. Now we've seen how binary can be used to store and represent a single number, but how can we represent more complicated data? The answer is to use formatted patterns of binary numbers. For example, if we want to represent a set 75, 84, 72, we can do this by representing each integer sequentially using a format where we have 1 byte to represent each integer. This byte represents the first integer 75, this one the second integer 84, and this one the third 72. Alternatively, we could also assign different meanings to the same pattern of binary data. For example, using these bytes we can also represent one unique character and give ourselves the letters KTH. The instructions for a CPU are simply patterns of bits or binary numbers formatted in a particular way and then run on computer hardware. The CPU, remember that the algorithmic logic unit is the heart of the CPU. It's a digital circuit that performs algorithmic and bitwise logic operations on binary numbers. It takes a formatted pattern of binary numbers transmitted through a digital circuit as input, and it performs the operation you request and returns the output also as a binary number. This is the schematic for a 74181 4-bit algorithmic logic unit with 75 logic gates designed in 1960. It can perform add, subtract, AND, NAND, OR, NOR, XOR, shift, and other operations. It takes a binary number A, a binary number B as input, and it returns a binary number F as an output. It also takes an operation code to tell it what kind of operation to do, such as addition or multiplication. Here in the schematic you can see A0, A1, A2, and A3 are the binary circuit or the digital circuits that give the binary number A, and B0, B1, B2, and B3 are the digital circuits that give the binary number B, and at the bottom F0, F1, F2, and F3 give the output F. Now let's look at an example of how formatted bit patterns can be used to make machine instructions that can be executed on a real CPU. Here we have a hypothetical example of a machine language specification for an algorithmic logic unit. It's a 20-bit format that is formatted first with an opcode, which we call S, of 4 bits, and then operand A, which is 8 bits, and then operand B, which is 8 bits as well. The opcodes are the codes for the operations that you want to perform. For example, to add two numbers, you would use the code 001, or to subtract the numbers 0010, to compare them and to move them, and so on. The operands are the integers that you want to perform the operation on. Now it's important to remember that physically these inputs are all digital circuits switched in an on or off state. Now let's imagine that we want to build an instruction to add two numbers. So we want to say 4 plus 5, and we want to compute this with our machine language. First, we would pick the opcode add. Add has the opcode 0001, and that's this 4-bit pattern here. Then we put operand A, so 000010, and operand B, 00000101. So that says add 4 plus 5. This is called a machine language instruction because it can be interpreted and executed by the CPU. A more human-readable way to write this instruction is to use assembly language, which is just written like this, add 4, 5. Instead of writing the opcodes and the operands in binary, we can use keywords that make more sense and the decimal number system that we're familiar with. Assembly language is a first attempt to make code more powerful and readable by humans. For a long time, programs were written mostly in assembly language. However, the transistors in a digital circuit can only operate on the machine language itself, the patterns of binary numbers. So what we have is an assembler program which makes one-to-one translations between the assembly language, which is a higher level language, than the machine language instructions. Because of this strong mapping, the assembly language varies strongly from one computer architecture to another. That means that the assembly language for one processor is often different than the assembly language for another processor. This concludes the lecture on computer architecture and machine language. Next, we'll see how high-level languages are related to machine language and assembly language.